Okay, so the pressure in a gas, so the idea now is to relate the pressure in a gas to the many collisions occurring with the wall, right? So we have millions of collisions with these walls, and that in turn produces a force, and that force is basically the pressure that we measure, that force divided by the area. And that would be the connection between the macroscopic wall, the pressure, and the microscopic wall, the velocity of the atoms. So let's look how this works. So to start with, imagine a particle that is coming to your right, collides with the wall, and goes back. So now we can calculate the change in momentum, right? The change in momentum, delta P, the change in momentum, delta P, or the impulse, delta P, which is equal to the impulse, that is equal to what? Is equal to the momentum, the final momentum minus the initial momentum, and that is equal to minus Vx minus nVx, and that is equal to minus 2nVx. Now, by Newton's third law, that impulse is minus the impulse on the wall, so the impulse on the wall is simply 2nVx. All right, so that is the impulse due to a molecule on the wall. This is due to a single collision. Now, if we have n of those collisions, then n of those collisions times the impulse on one wall would give us the total impulse on the wall. And you can already see here the connection. This is a macroscopic quantity, and this here is the velocity of a molecule. This is a microscopic quantity. So now, let's see how we relate that to the force, right? So remember from General Physics 1, the impulse is equal to F times delta T, right? That is the impulse. Now, the average force on the wall would be what? Would be equal to 2 times the rate of collisions. This is the number of collisions per unit of times the momentum of each particle. How do we get this? Well, the n of collisions, the n, remember, let's imagine that we have a box, right? And then let's look at this section of the box, and this is delta x, right? And delta x would be what? Would be equal to Vx times delta t. So any particle in this region moving to the right will collide with this wall in a time delta t. Any particle outside this region will not collide with the wall, right? So then we can write that, we can write, we can write that n collision, right? N collision, the number of collisions is equal to what? Well, would be equal to the number of particles in this volume, right? The number of particles in this volume is rho, the density, times the volume of this section here. But now I'm going to have as many particles going to the left as they are going to the right, so I have to divide this by 1/2. So, and this is basically 1/2. Rho is the density, is n over v, right? And v is just the volume. This is the volume of the whole box, and this v here is the volume of the section. I should write it like this. So the volume of the section is time the area of this wall times delta x, right? So that's the number of collisions, right? Now, times delta x times delta t, sorry, times delta x. That's the number of collisions, right? So the number of collisions then is equal to 1/2 n over v. A delta x then is Vx times delta t. And if I send this delta t divided this way divided, then I get the rate of collisions. This is the rate of collisions. And then I can put this rate of collisions here and I get the average force. Therefore, the average force, this would be equal to what? it would be equal to 2 times, right, 1/2 n over v a vx. Okay, I'm putting this whole thing here, right? The rate of collisions times n vx. And that gives me that that is equal to what? That is equal, this quantity here is equal to these two cancels. So I get that this is n over v, the volume of the box, times the area, times Vx squared times the mass. So that is the average force. This here is the average force on a wall here, right? So let's see what else we can do with that. We need to remember, let's just define what the root mean square speed is. So if a particle has velocity v, then that can be written as Vx squared Vy plus Vy squared plus Vc squared, the square root of that. That would be the speed of the molecule in 3 dimensions. So now if we take the average of all the molecules, right, the average square, then that we can write that as Vx squared plus Vy squared plus Vc squared average. But because these are independent quantities, I mean, there's nothing special about one coordinate axis, then we can write this average. We can basically break the average here. So this sum, this average sum here is equal to the sum of the average square, and this should be square, and this should be square here. Now, the root mean square is defined by, well, we are going to look at the fact that there's nothing special about the x-axis, so these numbers have to be equal for the three axes. So this implies that you're going to have a 3 here. So Vx average is going to be 1/3 of the average square that we're going to call RMS, the root mean square. And therefore, the net force that we had from the previous slide, this net force here, so now we're going to put here 1/3 of VRMS. We're going to put this right here. So when we do that, we get that the net force is equal to 1/3 the density times the mass times V squared, the average speed squared times the area. So this is the main equation to remember for now. And now the 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 pressure, then the pressure is that force divided by the area, right? So we take this force here, we divide by the area, and this is what we get. We get that the pressure is 1/3 of N over V M times VRMS. And this is the average speed of the particle, okay, of the particles in your box. So N over V is just the number density, and the average velocity of many particles traveling in random directions, remember, the average velocity is 0, but the square of the average velocity is not going to be 0. So VRMS is the root mean square speed of the molecules, which is the square root of the average value of the squares. It's this number here. So, but this is the important quantity here. This is the important quantity, and we have a relationship between the pressure and the velocity, the average velocity of the molecules. And this is the key to relate the microscopic world, the molecules, with the macroscopic world. This is the connection between micro and macro world. Okay, this is a quick question here. You have a rigid container that holds oxygen at 100 degrees. The average velocity of the molecules is greater than 0, 0, or less than 0. And it's 0. The velocity v is a vector. So you're going to have as many particles moving to the right as they move to the left, and then you're going to have an average velocity of 0. So this is 0. However, v squared average, this is different from 0 because this is a positive number, right? This is taking the modulus of every velocity and adding them, squaring them and adding them all. So therefore, you have to be careful with this little quantity here. This is 0, but this is not.